polar coordinates give us a very convenient way to describe certain curves and regions of the xy plane. And the way polar coordinates work is by taking the plane and dividing it up into circles. So here's the circle of radius 1, here's the circle radius 2, the circle of radius 3, so on and so forth. And the way we'll describe a polar coordinate is by using the notation P of r comma theta. Alright, and this polar coordinate is defined to be, in terms of xy coordinates, r cosine of theta, comma, r sine of theta. So this is a normal coordinate, so that's my x and that's my y. If there's a polar coordinate, then I'll write a p behind it to let you know that the first coordinate is an r, the second coordinate is a theta. Okay, so what exactly does this mean for us? Well, it's much easier to describe this just in terms of the r's and the theta if we've got these nice circles written, because what that tells us to do is take the angle, theta, whatever that angle is, and rotate it. So let's say that this is our theta, something like 3 pi over 4, 135 degrees. So suppose that's my theta right here. And then the r tells us how far out to go along that angle. So now once we've got that theta, we know we need to go out in this direction. And the r tells us how far to go. And so let's say that r was 3, we would go out 3 points. And so this is the polar coordinate for that r and that theta, where this distance here is r. Now, where does this formula come from? Well, that just comes from the fact that we're dealing with right triangles. So if this distance from the origin out to the point is indeed that r, and this is my theta, then we would get that this is my y coordinate, the vertical distance, and this is my x coordinate, the horizontal distance. And since we have this angle theta here, you could get that the opposite over the the opposite over the hypotenuse would get you sine for y, and the adjacent x over the hypotenuse gets you cosine for x. All right, so let's see this in at practice here. Let's take a look at a few different examples. So we're going to plot a few different polar coordinates, and we'll do it two different ways. We'll do it by just looking at the r's and the thetas, and we'll also do it by converting into x and y values. Okay. So this first one right here, this is my r and this is my theta. All right. And that would equal the xy coordinate. We'll take r cosine of theta, and we'll take r sine of theta. And so cosine of pi over 3 is 1/2, so 2 times 1/2 is 1. And sine of pi over 3 is root 3 over 2. And so those cancel to get you root 3. Okay, so let's plot this. We're going to go out 1, and we'll go up root 3, and that's between 1 and 2 here. So that would be roughly this point right here. But remember, you can also think of this as we're going to rotate through the angle pi over 3, which is 60 degrees. So here's pi over 3 right here. And we're going to go out 1, 2 units. So you can kind of see that if we go straight up here, that's 2. Then at this angle here, that would also be 2. So we have the xy coordinate 1 root 3 equals the polar coordinate 2 pi over 3. Okay, let's continue on with the other examples. Here we've got an r in my theta for root 2 and 3 pi over 4. That gets us root 2 cosine 3 pi over 4, root 2 sine 3 pi over 4. All right, cosine is negative root 2 over 2 here. Sine is positive root 2 over 2. And that gets us negative 1 comma positive 1. The root 2 times the root 2 becomes a 2, cancels with the 2 here and here. Negative 1, positive 1. Alrighty, so let's plot that. We'll go back negative 1 and positive 1, and we get this point right here. But notice that that is exactly the same as, suppose we had rotated 3 pi over 4, theta is 3 pi over 4, which is 135 degrees. So here's 3 pi over 4. And then we went out root 2 away from the origin, and that would get us this exact same point right here. So the point negative 1, positive 1, left 1, up 1 is the same as the polar coordinate root 2, 3 pi over 4. All right, continuing on, we've got r is negative 2, theta is 4 pi over 3. So that gets me negative 2 cosine 4 pi over 3 and negative 2 sine 4 pi over 3. Cosine of 4 pi over 3 would be negative 1/2. Sine of 4 pi over 3 would be, cosine of 4 pi over 3 would be negative root 3 over 2. Excuse me, no, I had that right the first time. My apologies. Negative 1/2, and then sine would be negative root 3 over 2. My apologies there. So now we'll just cancel the negatives here and cancel. That gets me a positive 1, comma, here, cancel the negatives, cancel the 2's, 1 root 3. And hey, that's actually the same point as what we had just a moment ago. So let's explore why that would be the case. So I claim that this is exactly the same point as the polar coordinate p of negative 2, 4 pi over 3. And why are these two points the same point? They have different coordinates in polar coordinates, but they are exactly the same. The reason why is because 4 pi over 3 is exactly 180 degrees, or pi radians, more than pi over 3. So if I were to actually rotate that much, I would get this angle here, 4 pi over 3. However, I was told to go in the negative direction. So instead of going out 2, I go back negative 2 and end up there at the same point. So far we've only had two different points. The first and the third polar coordinates actually overlapped at the same exact point. Let's do the last coordinate now. 4 comma 11 pi over 6. That's my r, that's my theta. Then we have 4 cosine 11 pi over 6. 4 sine 11 pi over 6. If it helps, you can think of these. This is 11 pi over 6. And since we're plugging into sine and cosine, we can just subtract 2 pi from it. That's the same thing as cosine of negative pi over 6, or negative 30 degrees. And the same thing as sine of negative pi over 6, or negative 30 degrees. And if we think of it that way, maybe that'll be easier. That'll tell us that the cosine is root 3 over 2 here, and the sine is negative 1/2 here. So I'm getting 2 root 3 comma negative 2. So I'll go out over 2 root 3, that's a little bit bigger than 3, and down 1, 2, negative 2. So here's my point right here, and 2 root 3, negative 2, and that's the same as the polar coordinate of 4, comma 11 pi over 6. And we can see that those are indeed the same coordinate. If we rotate 11 pi over 6, which is almost 2 pi, just 30 degrees shy of 2 pi, and then we go out from that point a distance of 4, we indeed get this point right here. You can kind of see how this is the distance 4, this would be the distance 4 at that angle. But remember, you can also think of this as negative pi over 6 instead of 11 pi over 6, because they give you the exact same angle, which will give you the exact same point, even though they actually have two different polar coordinates, technically speaking. So that would also give you the same polar coordinate, just like these 2 points were the same. Okay, so that finishes the problem. I've done probably a little bit more work than I needed to do, but I want to talk about why we get these 3 particular points in this problem. I want to also mention how do we know when our polar coordinates are going to overlap? How do we know we're going to get the same polar coordinate or the same Cartesian coordinate from different polar coordinates, the actual same location as we did in these cases? All right, and so it's a very easy way to figure this out. So if you have a polar coordinate, you have some r and some theta, then that'll be the same thing as the polar coordinate r theta plus k times pi. And here we're assuming k is even. And why is that? Well, that just means we're adding or subtracting 2 pi to the angle. And so if you have some coordinate, let's put it down here. All right. So here we have the distance r to the point, and here we have the distance theta. Well, note that if I add an even number of pi's, that means adding 360 degrees or some multiple of 360 degrees, then that would be the same thing as this. That would be theta plus 2 pi, which would be the same thing as that. That would be theta plus 4 pi, so on and so forth. You get the exact same angle out of it, so you end up getting the exact same point. And a similar thing happens if you add an odd number of pi's. The difference is your r needs to become negative. So here the k is an odd whole number. And the reason why is what we saw earlier. So let's suppose that this is my angle theta right here. So we're going to go out to our polar coordinate. All right. So this is what happens if we rotate theta and go out r. But if we add an odd number of pi's, let's say we add just 1 pi to it, then we get this theta plus another pi, and that would be positive r, but notice if we go backwards instead, negative r, that'll end up getting us the same point. And then if you add like 3, then that would just give you an extra, or add 5 pi, then that would give you an extra 2 rotations. So that's why we have these 2 formulas relating the different polar coordinates together.